had 4 people tell me they're not coming. I expect some others will get here a little late, as it proves a bit more of a challenge to get here than they perhaps planned for. So, let's see, there were a few comments I wanted to make. Hopefully, if you started looking at the homework that I assigned, you found it perhaps a little bit more straightforward than some of the problems in the book, and so you may be kind of wondering, I wonder what the exams are going to look like. My intention on the homework that I grade in the exams is not to kill you. I mean, I could with problems from the topics, but that's not my intention. It is to see, are you getting a basic understanding of the idea of groups and what we're doing with groups, basic understanding of proofs. Some of the harder proofs will be in the collaborative proofs later in the class, and that's why they're collaborative, so at least you have somebody to work with and kind of bounce ideas off of. Because certainly with a lot of the proofs, when we see them in a book, we see them nicely presented. We don't see any of the work behind the scenes of the failed attempts, the things they tried, oh, that doesn't work. Work a little here, work a little there, and it all fits together. What we see is the path from A to B to C to D, complete the proof, and it looks like, oh, I guess I'm just supposed to see that. And that's not what happens in mathematics. We have to get in there and struggle and work with it. Another way to kind of illustrate that is that there have been a few mathematical geniuses throughout history who did sort of just see things from A to D. And so one of those, let's see if I can pull up a movie trailer. I don't know if any of you have seen this.
That's a super easy way to tell.
We'll skip the ad in 3 seconds.
Let me prove it.
The Man Who Knew Infinity.
Oh, that's about
What do you see?
something more.
Imagine if we could look so closely, you could see it became fun. You see the patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian clerk, ill-educated in Madras, I would very highly value any advice you give me.
Letter for you. Postmarked England.
Yours truly, S. Ramanujan.
What does the S stand for?
Not himself.
You tend to write him here.
Don't forget me.
I could never.
Are you Ramanujan, by chance?
Oh, don't be intimidated. Great knowledge comes from the humblest of origins.
To the good of everybody, you should attend some lectures.
I'm here to publish. The letter only contains a small sampling of my discoveries.
This will take a lifetime.
Maybe two.
We need proofs of your work.
They are right, sir. I haven't completed that proof. How do you know? I just do. You don't put a study like that in my class.
How do you know that theorem?
Please, step 2-1, I do not know how to do. Where did you go? This is our home. Don't you know what I've given up to be here? I have nothing. You wanted to know how I get my ideas? Go on, speak to me.
There are no proofs. We just supposed to take him at his word? No, we're to take him at mine. Why do you do it?
Because I have to.
There are no proofs that can determine the outcome of matters of the heart. We are merely explorers of infinity in the pursuit of absolute perfection.
I owe you so much.
No. It's I who owe you.
And there are numerous people since Ramanujan's time who've really made their mathematical career, continuing to go through his notebooks and find proofs of formulas that he somehow just came up with, but didn't have proofs for. And as the trailer indicates, there were a number of people at the time, we can't believe these formulas without proofs. And he didn't really know how to produce those proofs. I'm sure there are some liberties taken with things, and it wasn't absolutely documented, but there were certainly correspondence, and he definitely had notebooks. In fact, I'm thinking somebody may have just found another one, a lost notebook of Ramanujan or something, that more to go through to figure out where he was coming up with these things. So that is not the way most people do mathematics. They explore, work with some things, and hope for some aha moments. So last time we were looking at some of the groups. Well, one more group example I think we should look at is what they look at in C. A plus B, they're defining strangely as A minus B union B minus A. And then they give a picture. Hey, anybody see any other way that maybe we might define that would give us the same set there?
A union B minus A intersect B.
A union B minus A intersect B. Now, that looks a little strange. You may just wonder, well, why aren't we just using union or intersection? I mean, A union B sounds so much easier to work with as a binary operation. So if we think of just A union B, for an identity, we need A union with something to give us A. Can you think of any set that union with any other set doesn't change the set A? So A union some other set. The null set. So in terms of an identity, the null set works. But in terms of an inverse, A union what is going to give us the null set?
A inverse, right?
Well, I mean, yeah, we're looking for an inverse. Is there anything that we can union with a set A that would, in fact, here let's think of a specific example, say just the set containing 1. What can we union with that set to get us the empty set?
Universal set minus 1.
Well, I mean, if we're doing the union, I mean, isn't A union B always going to contain A? There's no way we can get rid of elements when we're taking the union. And that's the reason they have modified from just the union, because with just the union, there's no way to get rid of the elements in A to get us back to the identity. So with just the union, we don't have the inverses. So somebody began to think, okay, how can I modify this to maybe get inverses? And this is what they came up with. And so in this one, A plus what gives us A as we start looking for an identity. Picture helps a little bit. So we have, or even this, I guess. A union what minus A intersect what would give us the identity, or give us A. Looking for an identity. Well, if it's going to work with all sets, I mean, in a certain sense, whenever we're working with sets and it's supposed to work with all sets, two likely candidates would be the universal set, you know, whatever the big set is, or the null set. So if we take A union to the null set, that's A. A intersect the null set is the null set. Well, we don't have to take anything away. I believe the empty set still works for us. What about inverses? Can we find A plus something that would give us the empty set? Can we take a set A, combine it with some other set, and actually now get us to that identity? A itself. A union A is A intersect A is A. From A, we take away A, we do get the null set. So for this particular operation, everything does have an inverse, and it's the rather interesting result that everything is actually its own inverse. No matter what set you've got, if you combine it with itself, a set union itself is the same set, the set union intersect itself is the same set, you take away that from itself, you are always going to get the empty set. So in fact, in this particular example, everything is its own inverse. So there's a fairly wide variety of things that can be groups. We've been looking at some examples of groups, but they all meet the criteria of there's an associative binary operation, and this does talk a little bit about the associative, that has an identity and every element has an inverse. Today what we want to look at is move on to the next chapter, which is chapter 4, and begin to think, okay, if we have a group, and we're not going to think about any specific group, but just we have a structure that is known as a group, can we come up with properties that are true just because we know we have a group? And in this chapter, I mean, we're now beginning to look just at the structure, not at any specific examples, but just because we have a group structure, is there something that we can say is true in this group or in any group? For it to be a group, there has to be an identity. I don't know if you kind of noticed, in none of our examples have we ever found a situation where there's more than one identity. There's always just one. Turns out that's the case. In a group, there is just one identity that we would call the identity. Up to this point, technically it should have been called an identity because we don't know if there is more than one or not. But a group has one identity, or the identity is unique. I mean, there are lots of ways this might be stated, but a group has one identity. And so this is a theorem or a property that's true in any group. Well, in abstract algebra, a lot of times when we see theorems, the first challenge is just sort of understand, well, what's the theorem saying? The next challenge then would be, how exactly do we know that's a theorem? How would we prove it? How would we justify that is really the case? This one, I think our understanding is fairly straightforward. We know there is an identity. This is claiming there is only one. So once we find one element that looks like it's the identity, it is, because there's only one element in there that looks like the identity. So unlike other instances, I don't know how many are football fans, but there was a Super Bowl last night to try to identify the best team in the league. And there would be some that might argue, well, after the game, it didn't identify the best team in the league, it identified the best, who played the best game last night. At another time maybe somebody else would be, and so, we start looking for bragging rights. It could be a situation where two people would have sort of equal arguments for bragging rights. Well, in the group, the claim is that there is just one identity. It has one identity. And so, if we think about, well, how would we prove this? We're going to do this idea a couple times, and so anytime we're interested in proving there's just one, well, suppose there are at least two. I'll call them, say, E1 and E2. Now, our goal in the proof is to hopefully discover, well, that can't really happen, that there really is only one. But in terms of trying to prove that there is only one, we'll at least allow the possibility maybe there are a couple. And just begin to work and push and see, well, what happens if we suppose there are two. Now, with our abstract proofs, our challenge is, we don't know what the group looks like, we don't know what the binary operation looks like. We're just given two elements. And so we got to sort of think very clearly, well, what do I know? What can I do in this problem? What do I know? What can I begin to work with? So anybody see what we can begin to work with here? Because at this point there's not a lot we know. Well, let's see. I mean, we're in a group, we have a binary operation, and I've got two elements. So, at this point, the only thing I can think of is let's consider E1 star E2. Two elements of binary operation. I know I can do that. At this point, it's not clear what I'm going to get with that, but in terms of looking at this, that's about the only thing I can think of. Okay, can we combine the two elements, and can we learn anything about the two elements? So as we think of E1 star E2, can we think of anything, figure out anything about that? Yes?
E1 star E2 equals E1 and also E2 because, yeah, anything times the identity is itself.
Okay, anything times an identity,
Yeah.
but yes. So it's E1 since E2 is an identity. But on the other hand, you're right. It's E2 since E1 is an identity. It's a binary operation. We always get just one result. We don't get maybe it's this, maybe it's this. E1 star E2 yields only one result. So E1 equals E2 must be true. So do we really have two different identities? We don't. If we've got two things that are acting both like the identity, well, they have to be the identity. And we'll use that fact in some later proofs where we may be kind of struggling to get a sense of what is the identity. If we discover an element that, oh, it's acting like the identity, an identity, well, then it has to be the identity. Now, another thing we've noticed as we've looked at some different tables, say, go back to this one. If we look across any row or any column in a group, no element is ever repeated in the binary operation. It certainly appears that A times, say, X and A times Y would be different as long as X and Y were different. Well, we're going to kind of look at the contrapositive of that and suppose if AX equals AY, can we prove then that x equals y? So this would be another theorem. Oh, and I mentioned contrapositive. I should probably talk a little bit more about that. In any if p then q statement, the contrapositive, if not q, then not p. And they have exactly the same meaning. I mean, if one is true, so is the other one. So as we encounter some proofs, sometimes we may struggle with the original statement, and the contrapositive might be easier to work with. So for this one, the contrapositive is actually if x doesn't equal y, then ax doesn't equal ay. Which, from looking at our tables, certainly seems to be the case. If you pick any first element and two different second elements, the result is always different. Nowhere do we get a repeat across the row. So it certainly would appear that if x and y are different, then ax and ay are also different. But given how little we know about groups in general, if we're looking at this in general, working with things that are not equal is a big challenge. I mean, there's lots of other things may not be equal, whereas in the contrapositive, where things now are equal and we're looking to prove things are equal, that's at least a more doable challenge. So, we kind of came up with this theorem in its contrapositive version, looking at our table. Different x and y's give us different results of ax times ay. But for proving that, we're going to look at the contrapositive. So, here's one where somehow we've encountered an element x and an element y where ax equals ay. And on this one, I just dropped the binary operation. If we don't see an operation in there, I mean, we are combining a and x with whatever the binary operation happens to be. We just don't want to write the symbol down this time. And our goal in this case is to somehow reach the conclusion that x equals y. Now, in our usual algebra that we work with, we know this is true, right? I mean, you cancel the a on both sides, x equals y. What we're trying, I guess, to figure out here is, in a group structure, does that cancel a on both sides idea still work, always work? And all we know is we have a group. We don't know what the elements are. They might be sets, they might be ordered pairs, they might be on Zn, they might be on our triangle, the motions of the triangle. I mean, we've looked at a number of different examples. We don't know. We just know we have a group. And actually, I should probably put in here, in a group, G. Because we do know we're in a group, and that is key to this whole proof is we are in a group. And we're looking at an A from the group, an X from a group, and a Y from the group. And we've got this. Now, certainly one might think, okay, boy, I don't know what the elements are, I don't know what the operation is. What can we do with this? Anybody have any ideas on what we can do and try? in a group.
Can we let A be the identity?
Okay, well, if A were the identity, yes, it works really, really quick. But I don't know that we know A is the identity. But an identity in there really, really helps us, would really help us. But I'm not sure we're at the point where we know that A is the identity. So,
Would we be able to subtract AY to the other side and set it equal to like 0 or a null set?
okay. Yes and no. So you're saying subtract A1. Well, when you say subtract A, can we phrase that more in sort of a generic group structure or group concept? Because you're thinking the operation was addition, and we're kind of working with numbers.
Okay, like we did earlier in set notation, AX minus AY equals null. Is that the proper way of phrasing that?
Well, even when we were looking for equal to null, in that example, we were looking for the inverse, right? I mean, in a sense, okay. Do we know anything about inverses? We are in a group. Everything in the group has an inverse.
Okay.
So we do know some things about inverse. We don't know exactly what they are, exactly what they look like, but everything in this group has an inverse. Which element do you think the inverse maybe might help us? A? So if I take A inverse, AX and AY are the same, so A inverse times an element, whichever name we use, the result should be the same. And we know A has an inverse. So there is an element in the set called A inverse. In fact, well, we can prove it's unique as well. There's only one that's the inverse. But I went to this first because actually I think that idea can come out of what we just will do here. So we multiplied by the inverse. We've got an associative binary operation, so we can regroup, right? And what's A inverse times A? That's the identity, right? That's what we mean by the inverse. It's the identity. And now we do have the identity times anything. EX is X, EY is Y. So we did need the identity there. We just didn't know whether A was in the first place. But if we multiply both sides by the inverse, we can proceed to do that. So we've got the associative, A inverse equals the identity, and the identity times anything doesn't change it. That's a property of the identity. So we have reasons now for every step. And here, in our attempts at doing something, we do have actually a reasonably linear proof, which is somewhat unusual. A lot of times you get in and play with things. Hopefully you have an aha moment that the pieces fit together, but sometimes it's more back and forth, back and forth.
Why does EX equal X and like not AX equal X? Just curious. Like what's the difference between E and A?
Okay. A is some general element in the group that we don't really know anything about.
Great.
E is the identity that we do know something about.
Great. That makes sense. Yeah.
And that's kind of our challenge as we are working with abstract concepts is, are there any of these elements we know something in particular about? And when it's a general A, all we know about a general A is it has an inverse. But we already group, every element does have an inverse. We do know that about A. For that A, there is an inverse. A inverse times A is the identity. The identity, though, is the one element we know even more about. The identity times anything produces the other element.
Cool.
So yes, at this point, we didn't know whether A was the identity or not. By this point, we do know we have the identity times X.
No.
So, now, with just a slight modification, or even maybe as a consequence of this, I suppose we could talk about the fact that A inverse is unique, or A has only one inverse. Because again, we could, as we do with identities, assume A had two, or consider A having two inverses, say B and C. AB is the identity, AC is also the identity. So AB and AC are the same. But we just proved if that ever happened, that A times one element equals A times another element, well, we really just were using the same element.
Oh, so we're using our previous theorem to prove that one.
Yes, yeah, so, yeah, so. And actually, I guess this theorem, I don't know if they give it a name, they may call it left cancellation. Because in a sense that's what we want to do, and the reason it's left cancellation and not just cancellation, in a group we don't have to have commutative. Maybe the operation's commutative, we don't really know. For this proof, we don't have to know. Okay. Well, let's think of another idea that ends up being true in every group. So suppose, in a group, G, we can talk about a product AB. Start with an A and a B and combine them. Question would be, what's the inverse of that product? Now, it turns out the inverse of this product is a little different than we might think. Just looking at it, anybody have a guess what you think the inverse is? If you were tutoring somebody and they really didn't know a whole lot of anything, what do you think they might say it is? A inverse, B inverse. Which you're all thinking, he said this was kind of a trick question. I don't want to say A inverse, B inverse. And the reason for that, well, it actually is B inverse, A inverse. The order is different than we might expect. Well, than we would expect.
Why does order matter?
Well, as we look at the proof, I think we'll begin to see why. In fact, suppose we went and thought it was it's A inverse, B inverse. We'd still be faced with the question, well, how do I prove that? How do we know if something's an inverse? To be an inverse, AB times its inverse must be the identity. And so AB times A inverse B inverse would have to be the identity. Can we make progress with this? I mean, it's associative, we can regroup, but if we are in a group, can we change the order? Not if they don't tell me it's commutative. I can't go changing the order, because if they don't tell me it's commutative, that is not a property of the group. I cannot just interchange the order on those two to get A and A inverse together and B inverse together. So that's kind of what fails here, but that doesn't fail here. So we're going to kind of start our proof here the same way. AB times B inverse A inverse. My hope is this is the identity, and if it is, AB times something gives me the identity. That something is the inverse, because there's only one inverse. So if I can find something that acts like the inverse, it is. This way, because it's associative, you know, I can regroup. Pull this B inverse over here. And this is associative, I can regroup. And here I can get B and its inverse together. And that's the identity. And anything times the identity is the other element. And now A times its inverse is the identity. And nowhere in this proof do we ever have to switch the order. We do some regrouping, but we can do that because it's associative.
What's wrong with that one?
Because this one, we like to swap A inverse and B. We can only swap if we know the operation's commutative.
And we don't know that.
And we don't know that in a group. So if we don't know we can swap the order, the assumption is we can't. But we can still come up with an element that we can multiply by AB to end up with the identity, and if we can find an element that works, well, that element is the inverse. So in this case then, since B inverse, A inverse acts like AB inverse, it is. And that's the advantage of knowing that there's only one identity and every element only has one inverse. If we're looking for the inverse and we're not quite sure, if we can find an element that acts like the inverse, that is the inverse. And again, this is a very abstract proof in that I don't know what the operation looks like, I don't know what the elements look like. All I know, I'm working in a group and they've given me an element A and B and asked me Okay, combine A and B. Can we figure anything out about the inverse? And the theorem says, yes, we can. The inverse of AB is the inverse of B times the inverse of A, or combined with the inverse of A. But the order does switch from what we would think. And the reason it has to switch is because as we go checking it, we cannot swap the order. We don't know if the operation's commutative. Another theorem that's sort of on the same idea as this, although maybe even a little bit more straightforward. What do you think is the inverse of A inverse? We take the inverse of the inverse. Yeah, we'd like to say A. Well, A inverse is the element that we combine with A inverse to get the identity. And yes, A works that way. So, I think we even said this early on as we were looking at groups and the idea of inverses. They kind of come in pairs. We may focus on A and find its inverse, but if we focused on A inverse, its inverse is the other one in the pair. I mean, they come together. And as this set example we just looked at, every element was its own inverse. That's unusual, but the inverse of every inverse takes us back to the original operation, or the original element. The order of a group, and I believe their notation for order looks kind of like the absolute value. It's the number of elements in the group. So if we look at some of our examples here, in fact, let me go back a couple. When we're looking at, say, Z sub n, Z4 was a 4-hour clock. How many elements are in there? This one's not a trick question. What? Okay. How many elements are in the original group? Aren't there just 4? I mean, in the table there are 16, because it's 4 times 4, but we're just considering 4 elements, right? Z5, we're considering 5. Now Z6, 6. Anybody remember when we were working with the triangle? How many elements we found as we were moving it around? I think we found 6, because we had do nothing, rotate once, rotate twice, or flip about any one of the 3 vertices. I think we had 3 flips, and in a sense 3 rotations. No rotation, 1 rotation, 2 rotations, because 3 rotations was the same as none. But I think we had 6 there. What would you say is the number of elements, say, in Z3 cross Z4? Yeah, this one would be 12. We've got 3 choices for the first element, 4 choices for the second, 12 choices altogether. Cooperate with me. So yeah, here's Z3 cross Z4. 3 choices for the first element, 4 choices for the second. Yeah, there are 12 altogether. 2 to 13. on page 39, A, 1, 2, 4, B, 1 through 4, C, 2 through 4, it's a little longer than I was thinking. Try to look at least some of those by the next time, and we may or may not. I had 2 days planned on this, and we didn't get started on this section till today, so we may or may not even start talking about the next topic the next time. We may just look at some of these problems the next time. But we'll definitely look at some of these. We'll decide how many we need to look at the next time. Let me quickly check. Okay. So I will see you Wednesday.